Welcome everybody to the 8th video lecture in Discrete Mathematics. So today we will be continuing our study in the proof techniques and in particular in the constructive proofs, and we will be looking at the case study proofs. So to recall, we want to prove a statement B from statement A, and there are various proof techniques that can be applied, namely constructive proof, proof by contradiction, proof by contrapositive, induction, counterexample, and existential proof. We will be looking at these various proofs one by one. Currently, we are looking at the constructive proofs. This problem comes again and again to your mind, and hence I will repeat it every video lecture where we talk about these proof techniques, namely which of these approach to apply. And let me tell it once again that it depends on the problem. For some problems you might be able to apply a particular technique, and for some problems some other technique. Some problems can be split into smaller problems that can be handled easily, while some problems can be viewed in a completely different way which can help us in understanding the problem easier. But whether to split a problem or not, and how to split a problem, and how to look at a problem, this is an art in itself, and that has to be developed by you. There are some thumb rules that we can provide you. We will be teaching you the various techniques and telling you the thumb rule, but at the end of the day, it is you who have to develop the skill of understanding which problem will require which application. And that can be achieved only by a lot of practice. Now, till now, we have seen things like how to split a problem into two smaller parts if the deduction that we make is an AND. That means if we have to prove A implies B and B can be written as C and D, then A implies B is basically same as saying A implies C and A implies D. So we saw this example which was saying that if B is an odd prime, then 2B square is greater than or equal to B plus 1 whole square, and B square is congruent to 1 mod 4. And applying this particular, splitting this problem into two parts depending on the deduction, we could split it up into two parts. Namely, first part, if B is an odd prime, then B square is congruent to 1 mod 4. And the second part, if B is an odd prime, then 2B square is greater than or equal to B plus 1 whole square. Now moving on, we also saw that there can be redundant assumptions. Namely, there can be some assumptions that are not necessary. Keeping those assumptions can only make the problem more confusing and complicated. So, if we can throw them away, it would be a big advantage for us. For example, if we can prove A implies B, and the assumption says that you can assume A and C, then clearly this assumption C is a redundant assumption. So basically the idea is that if A implies B, then A and C also implies B. So if the original problem was actually A and C implies B, then you can safely throw away C and solve the problem of A implies B. That might help you to simplify the problem, make your understanding clearer, and it will be a useful thing to do. Now, which assumptions that are needed and which assumptions are not needed, which assumptions to be thrown and so on, all depends upon your intelligence. In the sense that your experience and intelligence will tell us which one will be required and which one will not be required. So we saw the application of this particular thing in our problems. Namely, we had these two problems, part A and part B, and we applied both of them into this this particular removing of redundancies in assumption. In particular, we looked at what property of the odd prime, given the fact that B is an odd prime, what property of the odd prime do we need in either of the cases? And what we realized is that in the first case, all we need is that B is an odd integer, and second case, all we need is that B is a real number greater than or equal to 3. These are typical examples of problems where redundancies in the assumptions are not required. Now, we continued from here and solved these two problems using direct proofs. So we use direct proof, which is a special case of the constructive proof. And as I told you earlier, constructive proofs have two parts. Part A is what we call as direct proof. That means you directly prove A to B, or in other words, you message A to get B. The second one is case studies, and I will come back to this one particularly in the end of this video lecture. So we had used this direct proof for proving our two problems. So we gave you two problems, namely two problems and two different approaches. The first approach was, okay, work with A, keep on working with A, and whatever else is known to you, and you can output B. You can deduce B by doing a step-by-step deduction. The other option is going in the backward direction. It is because sometimes direct proof can be a bit magical and confusing. We have seen this particular example earlier in the earlier video, where a direct proof is not very clear how to obtain a direct proof. So in that case, we would like to use a backward proof. Now, what is a backward proof? The backward proof is nothing but you start working your way through B. In other words, to prove A implies B, the idea is to simplify B. Can we say, okay, we have to prove A implies B, now what does B mean, and let's keep on simplifying this problem. And basically it turns out that if you can finally prove that B and C are same, in that case A implies B is of course same as saying A implies C. And now that you have simplified C, it might help you to understand or get a full proof of A implies B C directly. So that is the idea of the direct proof. Either you go forward or go backward. So this is what we did till last video. Now in this video, let's start with one more special case that can arise. Namely, sometimes proving something that is stronger can be easier. Now what do we mean by that? Say we want to prove A implies B. But I know that C implies B. So if I can prove A implies C, then I may be able to prove, if I can prove A implies C, then immediately it will imply A implies B. Now the catch is that C can be a much stronger statement than B. It's possible that C is much stronger, so we might not be able to prove A implies C. So I am actually asking you to prove a harder statement to obtain A implies B. But that's what happens sometimes. Namely, sometimes we do come across problems where proving something harder can actually be easier. So let's look at this one example. So here is an example. It says that if B is a real number and B is greater than or equal to 2, then 2B cube is strictly greater than 3B plus 2. Now how to prove this number? Let's see. So, first of all, we know that b is greater than or equal to 2. That means b cube is greater than or equal to b square. This only follows from the fact that b is greater than or equal to 1 actually. And now, since this is true, therefore 2b cube to prove 2b cube is bigger than or equal to 3b plus 2, this is what we have to prove. To prove this line, it follows from the fact that if we can prove 2b square is greater than or equal to 3b plus 2. Now note here that this statement that 2b cube square is bigger than or equal to 3b plus 2 is actually a harder statement to prove. But we are saying that okay, if we can prove that harder statement, then the previous statement, which is what we want, will follow. So the implication here is not if and only if, unlike what we saw in the last case where we were removing assumptions, but here we are making the problem or our goal harder and harder. Now to prove 2b square is greater than or equal to 3b plus 2, this is same as, of course, b square plus, now I have just basically taken the b in the other side, so b square plus b square minus b is greater than or equal to 2b plus 2. Now, once again, note that this b square minus b is greater than 0. Why? Again, by the same logic that since b is greater than 2, so b square is greater than b. So b square minus b is greater than 0. That means I can remove this positive term on the right hand side. Sorry, on the left hand side. In other words, I am saying that remove a positive term and still can you prove this statement b square is greater than or equal to 2b plus 2. Again, note that this line is actually a harder line to prove than the previous line. But the reason I am doing it is that this line now, as you can see, looks much more tractable. It doesn't have a cubic expression and it's pretty neat at this point. And as you can kind of guess here, that this is doable in the other words. So this follows from the fact that b minus 1 whole square is greater than or equal to 1, from which it follows that this follows from the fact that if b is greater than or equal to 2, we have the result. Right? So in other words, we could go in the backward direction, or not backward direction, rather we could simplify, make our problems harder and harder and harder, and yet at the end we could get a solution. The reason is that once we made the expression doable, it was easier for us to prove, although the problem as such became harder. So the trick here is that there are hard problems or harder problems, and then there are problems which you can solve. Sometimes solving a harder problem can be easier, and hence converting a simpler problem into a harder problem can mean the actual trick. Right? Okay. So moving on. So the technique so far that we have seen till now is that to prove A implies B, we can either split up the problem into two smaller parts depending on whether B can be split up as C and D. We can see that if we can reduce B or not reduce, we can find out a C which is same as B, then proving A implies B is same as proving A implies C. We also prove that if C implies B and we can prove A implies C, then this is enough to prove A implies B. That means making it harder can be actually easier sometimes. So this is the kind of the technique that we have learned so far. Now in the rest of the video, I will be going into a new way of splitting the problem. This depends on splitting it according to the assumptions. So in other words, sometimes the assumptions can be split into different cases. And in that case, we will be able to split it up into smaller problems. For example, again, if we have to prove A implies B, and A is C or D, then A implies B is same as saying C implies B and D implies B. Please prove it for yourself that this statement is indeed correct. Use the propositional logic technique that we have done to check that this is indeed correct. So for example, let's start with this example that we have here. If A and B are two positive integers, then prove that A square minus 4B cannot be equal to 2. Now, how do you split this problem? First of all, we have to understand what is the A and what are the B. Now, what is the A here? The A, or the set of assumptions, is A and B are two positive integers. Okay? Doesn't seem to be a very natural way of splitting it up, or is it? Okay, we will see. And what is the deduction? Deduction is that A square minus 4B cannot be equal to 2. Now, this is what we do. Okay, so this is another way of stating it. That is, this problem says that A square is not congruent to 2 mod 4. Recall your number theory notations, that if I say that A square minus 4B cannot be equal to 2, which means that A square minus 2 is not divisible by 4, or A square is not congruent to 2 mod 4. Now, to start with the proof, as I told you, I would like to split the assumptions into cases. Now, this is the first of its kind maybe you are seeing, and therefore I am going to do it fully here. I will give you a few set of problems on this line that you will be asked to solve for your exercise. You will also of course get an assignment at the end of this week, which will include all these kind of proper questions on this subject. So, one way of splitting it up is that so if A is a positive integer, and if divide by 4, what are the possible remainders? Now the possible remainders are, of course, 0, 1, 2 and 3, right? So if I have to prove this particular statement, that is, which is basically means that A square is not congruent to 2 mod 4, then it is same as we can solve it by case basis. Or in other words, we can say that, okay, let A be the integer that is divisible by 4, for which means that the remainder is 0. Then can I prove it? Secondly, second case will be if A when divided by 4 has remainder 1, can I prove it? That will be second case. Third case and fourth case similarly for remainder 2 and 3. So that is basically the plan. So we split the problem into 4 cases depending on the remainder when A is divided by 4. So the cases are, as I told you, case 1, case 2, case 3 and case 4 depending on the remainders of 0, 1, 2 and 3. Now when we have this, we can do a case by case basis. So we can take the case 1 and solve it. So let's start with it. So the case 1, we know that the remainder when A is divided by 4, it has remainder 0. Or in other case, A is equals to 4R for some positive integer R. Now let's see, in that case, can you prove something that A square is not congruent to 2 mod 4? Possibly, let's see. So A square is equals to 16R square just by squaring it. And therefore, if I take any 4B, so A square minus 4B is 16R square minus 4B, which is 4R square minus B. Now, since 4R square minus B is an integer and 4 times an integer can never be equal to 2, therefore 4 into 4R square minus B can never be 2. Or in other words, A square minus 4B cannot equal to 2 in this particular case. So this proves us that if A is divisible by 4, or if A has remainder 0 when divided by 4, then we prove that A square minus 4B cannot be equal to 2. Now you don't need to look at the rest of the video at all. You can just try to solve your problem you can solve the other 3 cases by yourself. For example, for the case of case 2, that is when the remainder is 1, then what can we say? Again, we can say that A is equals to 4R plus 1 for some positive integer R. Again, let's do it. What is A square? A square is 16R square plus 8R plus 1. So A square minus 4B will be 4 times 4R square plus 2R minus B plus 1. Now you can already see that this is a 4 times a number plus 1. So this is an odd number. This is not an even number because 4 times a number is an even number plus 1 is an odd number. Thus, this number just can never be 2. The same way of saying is that 4 times this number can never be 1. And so we have that A square minus 4B cannot be equal to 1 even in this case. Let's go to the case 3. In the case of case 3, the same thing. We start for the case where A has remainder 2 when divisible by 4. In that case, A is equals to 4R plus 2 for some positive integer R. And now if we square it up, we get some 16R square plus 16R plus 2. Actually, yeah, that's right. I've done it right. And now if I do this A square minus 4B, this is 4 times 4R square plus 4R plus 1 minus B, which is again, if you realize, same thing as the first case where it is 4 times an integer and hence cannot be equal to 2. Right? So this is again a 4 times integer and hence cannot be equal to 2. And now this brings us to the last case, which is the case where the remainder is 3. Again here, A is equals to 4r plus 3. So A square is 16r square plus 24r plus 9. Now, here, if I subtract it, you have to break this 9 as 8 plus 1. And then you realize that this is 4 times 4r square plus 6r plus 2 minus b plus 1. Again, it is a 4 times a number, integer, plus 1, and hence this cannot be equal to 2. Thus, we have broken up into 4 cases, and for each of the cases, we have proved that the statement a square minus 4b cannot be equal to 2. So this concludes the whole proof. So to complete the proof, we first ensured that we split up the assumption into 4 cases. Now this is something very important. We had to ensure that these 4 cases are the only cases. Can there be any other cases? No. In this case, it is very easy to convince that there is no other case. So in other words, if A is a positive integer, then when it is divisible by 4, the only remainders left are 0, 1, 2 or 3. Thus, we have exhausted all the cases. This is a very important thing to check always in case studies, whether all the cases has been considered. And then we solve the problem in a case-by-case basis. Right? And we prove that for each of the cases, it cannot be equal to 2. So this is a typical case study problem where we split the assumptions or split the problem depending on the assumptions. We will see more of this particular technique in the next video also. Okay. So this brings us to the end of this video lecture. Thank you.